Thank you, Nisha. Um, Tēnā koutou katoa. So my name is Maxime Rio, and as Nisha said, I'm working as a data scientist at NIWA and also as a data science engineer at Nesi. And today it's my great pleasure to give you to present this webinar and to give you some tips and tricks around Jupyter, in particular Jupyter on Nesi. So the menu for today, first I'll give you a brief overview of what is Jupyter as it is installed and configured on Nesi. And then we'll see three tips. So first one will be how you can customize the kernels that you would run in your notebooks using a tool that we developed and called nesi-add-kernel. Second tip will be about how you can run the very same notebook that you've developed interactively in a non-interactive way using a tool called Papermill. And the last tip that I like to present is how you can leverage an extension of Jupyterlab called Jupyter Server Proxy to access web application that will be running in the same session. A typical use case will be a tensor board or maybe a Dask dashboard, for example. But before we dive into this, a bit of advertisement. So at Nesi, I have the great chance to be part of the computational science consultancy team. So Chris, Scott, Alex, Pletzer, and I are helping the researchers that are working on the Nesi HPC platform, and we try to make their code work better and faster. So if you feel like you could be interested in having our help to maybe port some code from CPU to GPUs or benchmark it and optimize it, also help you to develop some workflows. We are here to help, so don't hesitate to contact us at support@nesi.org.nz, and we can see how we could collaborate with you. So on this note, I will start with a quick presentation of what is Jupyter on Nesi. So first, so it's a service which is provided at the following address, so jupyter.nesi.org.nz. I won't do the login here during this demo, but so I'll explain a bit how it works. So when you start and you log on the website with your Nesi credentials, the first screen you will face will be the server options screen, and there you can select multiple options for your session. So the project, which project will be charged for the computing here, how much time you will run the interactive session from half an hour to 8 hours maximum, number of CPUs, amount of RAM, and possibly some GPUs if you want for this interactive session to use a GPU. I want to say that this will be your default instance, but once this was in running, you can also ask for 3 more sessions, interactive sessions that will be named. If we have time, I can show you that during the demo or after. And for these other sessions, you can also request some different resources. So for example, if you started a long session, but really just to interact and see some data, but now you want to try quickly something on a GPU, you can ask a short separate session for that. One more note about the GPUs. So at the moment, we provide 2 types of GPUs. One are the P100, so our old generation of GPUs, but you have to be aware that it's a limited resource and they are shared with the rest of the HPC, of the Mahuika, to be more precise. Which means that at the moment you're asking for P100, unfortunately, maybe none are available in that case. I mean, your session won't be able to start. Another thing that we're experimenting at the moment, so it's very new, hence the new sticker. We provide a slice of A100, so it's not the full GPU, it's a 1/7 of A100 GPU, so more limited in terms of computing resources and less memory. But for this one, what we tried to do is to ensure that they are more available by setting aside some resources for this and making sure that people can use only one of them at a time. So again, we can't ensure you that you will have one when you request one, but we make sure that they are more available. And we welcome any feedback about this one if you have the chance to try them, because again, that's sort of a little experiment we're having at the moment. Okay, so once you've selected your options, you will press start and it will start your new session, and you will be facing Jupyterlab, so that's sort of the default interactive environment. And I want to mention that on top of Jupyterlab, we are developing other interactive services, which would be still considered as beta version at the moment, But again, we welcome any feedback around these ones. So we have a virtual desktop environment, which will be a full-featured graphical Linux graphical interface. They also have RStudio and MATLAB. But for today's session, I will mostly focus on Jupyterlab itself, and in particular Jupyterlab in the context of it will be heavily focused on Python, even if some of the advice can be used in other contexts, of course. So for about Jupyterlab, for people that maybe are not too familiar with this interface, of course it can execute, well, display and execute notebooks, which what you see in the center of this image. But I want to emphasize that it's not only that, you can also use it to browse your files and have a nice preview mode. So if you want to check some result images, for example, from your computations, I personally find it very practical. It has also a text editor which can be bound with a console for auto-completion interactive coding, and a terminal also, which is very practical, and we'll see that in a few minutes. But okay, so then I'll introduce the first tip, and before we switch to it, I just want to mention one small thing is here, you may see in this top right corner, this papermill_demo, and this is actually what we'll call a Jupyter kernel. So it specifies under which sort of environment your notebook will run, and that's not a default one. We'll see how we do that. So now we switch to how do you customize a kernel to execute your notebook and make sure that it can run with the software you want. In terms of software stacks, so on Nesi, you have many options when you want to run any type of code. So maybe the option people are most familiar with are the environment modules that have been prepared by the Nesi team, and so the software will be pre-packaged, compiled, and optimized for our platforms. Typically, you can find different versions of Python, of R, of MATLAB, and many softwares. But let's say you want to install something which we don't provide, and if you're a Python user, for example, you like Python virtual environment, and you want on top of the environment modules of Python to pip install some extra packages. So that's another possibility to sort of install by yourself packages. Another type of software stack you may want to use are Conda environments. So in that case, you will use the mini Conda environment module and use this one to create from scratch your software stack, including exactly which version of Python and which version of numerical libraries, for example, you want. The last option I'd like to mention here are containers. So if people are familiar with Docker containers, unfortunately, on Nesi, we don't provide support for Docker container, and that's a similar story in many HPC places, because you would require admin rights, which we don't really want to give you on the whole HPC. But there is an alternative solution, which is Singularity containers, and there's a very nice bridge, so you can actually pull the Docker container as a Singularity container. So there are many options here in terms of the software stack you may want to install, but the question will be, how can I make sure that my notebook, which I'm developing, will leverage the software stack I've prepared? And this is where customizing the kernel comes into play. Just one more word a bit about what is exactly a Jupyter kernel. So you can think about it as a separate process which will be running under the hood, and every command that you will enter in the notebook will be read by this process, interpreted, and the result will be displayed back into the notebook. So typically, again, in the Python context, that will be the Python interpreter that will be run under the hood in the Jupyter kernel. And how kernels are defined. So we provide a set of default kernels, and we'll also use this during the demo time. But let's say you want to create your very own kernel. The first thing is you will need to create a folder under your user home. So in local shared Jupyter kernels. The folder will be the name of the kernels. Inside of this, you would have a kernel.json file, which have a bit of configuration, some icons files. And the main point here is to do all the specific configuration for your kernel, you will need to write a wrapper script. And this wrapper script, for example, will preload some environment modules to make sure that you expose the right interpreter. It's Not complicated, but it can be a bit tedious, and if you do some mistakes, then it can be complicated to debug. So my colleague Chris Scott and I, we decided to write a tool to automate this and simplify our life, and hopefully your life too. So it's called the nesi-add-kernel, and it's already provided as part of the Jupyterlab module. And what it does is it will take into account these typical use cases where, for example, you want to preload an environment module before running your kernel. Well, typically, maybe you want to preload the CUDA drivers or the cuDNN library. Another one is maybe you want your notebook to run with the interpreter, which is defined in your Conda environment. So how do you do this? Another case is also maybe you want to do it the same for Python virtual environment or Singularity containers. And finally, if you happen to define your software stack environment in a shared folder, let's say your project folder, and you have other colleagues working on this one, then you can also expose it as a shared kernel. So one person configure it, but everyone under the same project can use it. If you want to know more about this, we have a dedicated page on our support page. And also the code is available on GitHub if you want to have a look at it and see how the magical sauce is done. Just to give you an idea of how does the interaction works. So again, 99% of the time you would not need to load Jupyterlab, because if you're doing it from the Jupyter instance on Nesi, this is already loaded for you in the terminal. Then you can, as a usual command line interface tool, you can do a -- help to see what are all the available options. And here I'll just highlight two of them. So let's say I want to use the interpreter, which is defined in the environment module called TensorFlow, which encapsulate also a Python interpreter. So I would do nesi-add-kernel, name of my kernel, and then the modules I want to preload in my kernel. And you can add multiple of them. Or a second example is, let's say I have already created a Conda environment and a specific path. So I could do nesi-add-kernel -p, then the path of my Conda environment, and again, the name of my Conda environment. And I feel like the best way to illustrate this now is to do a little demo and hope for the best. Okay. So, as I said previously, I already prepared a Jupyterlab session, so we won't have a look at how do we start this. So it has already been started on Nesi. And when you start your session, you'll likely see this first screen, the launcher screen, and you could see all the pre-made kernels. So the goal here will be, let's try to add one more here and use it in a notebook. To illustrate a bit of a use case, so I've prepared a notebook which does, and that's for illustration purpose, that try to fit a neural net using Keras, and Keras, which is built on top of TensorFlow. I won't go through every step of what the notebook is doing, but if you want to have a look at it later, so this is also available on the Nesi GitHub. For this first step, the important point is the fact that I want to use TensorFlow, and actually I want to do something a bit more fancy. I want to try a couple of hyperparameter combinations of my model, so I want to use Keras Tuner. And let's say it happens that maybe it's not available in a module on Nesi, or for some reasons I would prefer to install it myself as a Conda environment. So here I could select a kernel, but there's no kernel that satisfies my need at the moment. So what I'll do is I'll create the Conda environment. Well, I'll pretend, because it takes a bit of time, so I'll just show you how it would have been created and how we register this as a kernel. So here I'm in the in this terminal, I'm in the folder where my project is living, and on the left here up, that's the folder. And I have already defined a Conda environment file in this environment let's increase it a bit, .log.yaml. And to create it, I would have to load the mini Conda modules and do a conda env create -f to specify that I want it to be created from this environment file, environment.log.yaml. And here I would create it locally in a folder. So let's say I want to create it in the vm_tf folder. If I do this, I'll just press to show you that this can execute unless there's no typo. And that will actually create my conda environment, and there will be a new folder here. Again, just to save a bit of time, I'll just cancel this. And let's pretend it worked because actually I have a VM folder which is actually exactly doing this. Just one quick note about Miniconda. If there are people that really like this sort of environment, I would like to point to our support pages. So we have, and let's see, we have a page with tips and tricks around Miniconda, which is good to be aware of if you want to save space and avoid, for example, using too much space in your home. There's a couple of information in that page. Okay, so as I said, so now I have my conda environment, which is ready, and I want to register it as a kernel. So first I would load the Jupyterlab module. And as I said previously, very likely you don't need to do it unless you've done a module purge before, for example. Then you will have access to the nesi-add-kernel command, and we can have a look at what are all the options doing --help. So you can see, let me scroll up. So we can see that we have all these options to add a conda environment, a virtual environment, a container. Even you can add some arguments for your container. Let's say you want to expose, for example, then the GPU will need some additional arguments here, or you can share the kernel. So I'll use Control L to clear my screen. For now, what I will be doing is I will register the current folder, which is a conda environment, so .vf. And I will call it paper meal demo because that's the name of my current project. What it will be doing under the hood, it will prepare my wrapper script and it will do a bit of testing of this wrapper script. What is important to note here is, okay, maybe if there is a typo, it will crash and something wrong will happen. And the message that you will get at that step, this is the one that you will likely want to copy and paste in a ticket for Nesi. So if you want us to help you to debug this, so it's very important to capture this part if anything goes wrong. So now you can see that, okay, hopefully the demo went well and it has registered it. One more thing is if I want to interact with it or remove it, there is another tool which is already provided by default by Jupyterlab, which is Jupyter Kernel spec, and you can use this one to remove the notebook. So if I go back to my if I go back to my notebook, you can see that okay, now it has appeared. If it does not appear right away, a good thing to do is actually you can reload the whole page, the web page, and it will refresh actually the list of the kernels, and you have access to it. So now I will load the first. I will run the first cell and we'll see what happens and actually if it finds the dependencies. I should have mentioned that, of course, the conda environment I've prepared have these dependencies. So, okay, it's working and there is a weird warning, but it says something about a missing library. So let's ignore it for now. So the first thing I'll be executing here is I have a bunch of parameters. So as I said previously, this notebook is fitting a small neural net, but I want to try multiple configurations. And here I define the sort of how many epochs I want to run it on or try also. If I put it in small numbers, it means that it will be very fast to run, and that's good for interactive usage. So I load the data. For people who are familiar with machine learning, this is the well-known MNIST dataset, so some images of digits that we want to classify. I create a function to have my small neural net defined, and let's build it. And then I have, oh, wow, that's a lot of warning. I'll pretend that I'm surprised, even I'm not at all. And if we look at it a bit closely, we can see that it's unhappy about the lib kublas. And then it's a good time to realize that actually maybe it won't be using the GPU I requested it. Because actually, when I started this session, I requested one of the small A100 GPU I mentioned earlier. So, and that's normal because when you want to use a GPU, you need to preload the CUDA driver. And especially if you want to use with TensorFlow, you will need to preload also the right version of cuDNN. Okay, so let's recreate this kernel, but now we'll make sure that we preload the right module at the same time. So I'll go back to the terminal. First thing is, actually, I will delete my kernel. So I'll reuse this command. Yes, I want to delete it. Up, let's clear it. And thing to know is we have many versions of CUDA and cuDNN available, so it can be a good thing actually to have a look at what is available and to pick the right version. And for people maybe that are less familiar with TensorFlow, TensorFlow is a bit picky about which version it wants to run with, so you have to pick the right one for it to work. So if we do module spider, it will list all the available modules that match this query. I have to mention also minor things, but on Nesi, you need to use the QDNN with uppercase DNN. We also have one with lowercase, but this one won't be working well. And okay, so I see that I have many versions, and I know, so I've installed TensorFlow 2.8 in that case, and I know that it's compatible with this QDNN. So that will be the module I need to actually add to my to the definition of my kernel. So I will just use the upper arrow to find again the command I've been using to create my conda environment, and then I will append. Oh, I need the C here. I will append this module in addition. And what will happen now is in the wrapper script that defines the kernel, it will at the same time load cuDNN and CUDA, and also make sure that the Python interpreter in the conda environment is used. So let's go back to the notebook. Up. And actually, I will clear it. Let's see if I can. Yeah, let's restart and clear all outputs. And let me double check. Are we doing good at time? Yeah, that's okay. With red. Okay, so now let's reload and see if we still have these warnings. And if not, if it's successful at using the GPU, we should have some message at some point that says, hey, I found the GPU and I'm using the right one. So I'll just quickly rerun the first cells. Uploading the data, creating the model, building a dummy model just to see how things are going and if it's finding the right resources. And yes, here I'd like to highlight this string, which is a very good sign. So it means that actually TensorFlow has found our GPU and is capable of using it. So hey, we can proceed and make sure that it will be properly accelerated in that case. I will quickly run the last cells, which are actually doing the hyperparameters optimization search with a random strategy up. So here we define the search and then we run it. It will train a bit, and in that case, because I want it to be, again, for interactive usage, I don't want to use a large amount of resources. So I keep it low just to make sure that code is working, not that it's giving a good results. So it should be about to finish. Okay, it takes a bit more time than I thought. Okay, done. And once it's trained, I'll take the best model found so far, and I will run it on the test data to see what's the performance. And we have 90% accuracy. Not too bad, not great, but again, I just wanted to make sure that the code is working, not that I get the best model I could. That will be for the next session. But for now, I will pause to drink a bit of water and see if there is any question.
We've just got a question right now. What happens with the active notebook when you remove the kernel it is running? And Matt has attempted to answer it, but Maxime, please go ahead.
Yeah, not sure I've given a clean answer on that one, Maxime, so try that.
That's a good question. It's not something I don't believe it will crash, but to be fully honest, when I do these sort of things, I ensure that actually I don't have any notebook running or I don't expect them to be functional anymore. Yeah, I should probably give a try to this and to give a better answer. Is there any other question?
Nothing in this session. The rest of it was all answered.
Okay. So, okay, so I'll continue with the next point. So here, what I was saying in this, so in this context, I've been running my notebook with very few resources, again, just to make sure it works. But let's say I want to scale it up. So instead of running it for 2 epochs, which is very limited, I want to run it for many epochs. I want to run it with many hyperparameter configurations to make sure I have the best model. But maybe if I do this, I will hit the time limit of my session, or maybe also here I've used these tiny GPUs, but my model actually would be much better on a very large, the full A100. So to do this means I will need to run the very same notebook, but I will need to have it to run as a Slurm job. And this is what we'll have a look at now. So let's resume presentation. So this is where we'll introduce another tool called Papermill, and which is a command line interface tool. Command line interface tool, which will let you do this. So just a quick explanation of what is Papermill doing. So you take a notebook and you can annotate part of your notebook, so actually a cell, to say, hey, that cell will contain the parameters of my notebook. So now we'll have a parameterized notebook where you can actually, from the command line, you can inject new parameters. You can change what at runtime will be executed. The first step is find the cell where you define all your parameters, click on the cogwheel icon on the right of Jupyterlab, enter parameters here to say to tag this cell, so that will go into the metadata of the cell. So tag them as parameters, and then save it. Then the trick will be to use the Papermill command line tool. And here there are a couple of things you can do. So first, so it will render and will run non-interactively your notebook, and it will save the results. The first thing, you can specify a kernel. So you can say, hey, Papermill, I want for this notebook, I want to use this kernel that you already prepared, or another kernel. So that's the first interesting part. Second very interesting part, as I was mentioning before, is you can inject some values for some parameters. So you can replace what was defined in your notebook with new values. And for me, that's what makes it very appealing for transitioning from interactive workflow, where you make sure things work, to a non-interactive, where you make sure that things are scaling. So there are multiple different syntax to inject parameters. The one I'm highlighting here in red will be that you put the name of the parameter and the value of the parameters. It's interesting to know that there are other options, like you could actually define all your parameters in a YAML file and inject the full YAML file, for example. Then you'll provide to this command line tool the input notebook, and you tell it where to save the results, so the output notebook. There are many other ways to use it, but that's probably the most straightforward way to use it. And here on the right, we can see an example of a rendered, so a notebook which has been executed and saved. And you can see that it has introduced a new cell. And in that case, I was injecting the result file parameter, because for this job, I wanted it to be saved in another place, for example, and it has replaced it. It's interesting to note that you can only annotate one cell as parameters, so I strongly advise that you regroup all your parameters in one cell at the beginning. Naively, at the start when I was learning this tool, I was trying to annotate multiple cells with parameters, and that won't work. So just one cell, all your parameters are regrouped there. And yes, and once you've done this, so that's only solving half of the problem of, okay, how do I run it non-interactively on the Slurm, so on the HPC. The next part is you need to wrap this into a Slurm submission script, which for people that may be less familiar with what it is, it's a bash script. But with a special thing, which is a header, which is here labeled as the important stuff, where you will use some commands to instruct Slurm, the scheduler, what are the resources you want to use. So for how long, so how much time, how many CPUs, what's the RAM, which GPU you want to use. You can ask all sort of things to the scheduler, even some very cool things like, hey, can you email me when the job has started, or can you email me when the job has stopped or finished? If you want to know more about the Slurm submission script and these sort of things, so I won't go into all the details today, but Nesi provide trainings on this, and in June there will be an HPC carpentry hands-on workshop. So the registration is not yet open as far as I know, but I strongly encourage you to register to our newsletter so you get notified as soon as registration opens. Okay, this being said, I'll show you a quick demo of how does that look like within the Jupyterlab environment. So just to continue with the same notebook, so this is the cogwheel I was mentioning in the slides. So if we look here, actually I've already tagged this one, but let's pretend it has not been tagged. So that will be what you see. And then to tag it, you click on this cell, you enter parameters, up, you press enter, and ta-da, that's it. You don't have anything else to do. Well, apart from saving your notebook, and then it is ready to go. Then I'll show you what is the equivalent Slurm script. So here I've defined a couple of resources, and for this one, for example, I would like it to run with a bigger GPU, so I want to run it with the A100, for example. Then I have to mention a small thing here. In that case, I've defined Papermill. So the tool is installed as part of my Conda environment. It's not yet available as a module at Nesi, but the next release in a couple of weeks of Jupyterlab will have Papermill included in it. So this boilerplate code will reduce to modulo Jupyterlab instead of using a third-party Conda environment. So then I have my command line call of Papermill. I reuse the same kernel that I defined previously, the Papermill demo. And here, this is where I want to scale up. So there are 3 parameters to my notebook that I wanted to change. I wanted to have more epochs for the training of my model, a large number of trials to explore more hyperparameters, and I want to have a slightly larger neural network, so the maximum units I want to explore. There are a couple of other options that are possible, but I won't go into the details now. Then my input and the output. So once your Slurm submission job is ready, you can go back to a terminal. Let's clear it. And to interact with Slurm, the first thing to do will be to use the sbatch command to submit your batch job, and then you point it to the script. And here, in my case, it's defined in the Slurm folder. So it will be the fit Keras model. Once you've done this, you will be given a job ID, and you can use the sq command to actually look at, okay, where is it in the queue? Has it started yet or not? And you can see now that it's pending. It has not started yet. I'll show you a results which I've pre-computed, so we don't have to wait for this one to be scheduled, and we can finish on time and everyone have lunch at 12. But for now, I'll cancel this one also because we don't need to run it. So to cancel a job, you can use scancel. I'll just double check that it's okay. And the other one, oh, actually, that's a small digression, but the other one is my current Jupyterlab session. So even the Jupyterlab session, which are interactive in the web browser, are a Slurm job under the hood. So let's have a look at what will be a typical results from the executed Papermill notebook. So that will be this one. Up. So this is the executed one, so the one which have been saved by the job. And what you can see here is this is the core thing, the main the main cell which has been injected, so added by Papermill, and you can see that it's changed the values. Then the rest of the code will be the same, but actually, well, using these new parameters. And if I skip almost everything but go to the end, we can see that the that was the hyperparameter search, and trust me, here we have trial 20, so actually tried more configurations. And if we look at the final accuracy, we have 98% accuracy compared to the previous 90% accuracy. So it found a way better configuration of parameters, and that's all good. So that's it for Papermill. I don't think I will say anything more. I'll skip to the last part of the presentation, and then we can pause to have to answer some question if there are any. So once we have done this is great, but actually I'd like to see some a few more things about my model, especially if you're using TensorFlow. There's a very cool tool called TensorBoard, which is a web interface that can let you actually investigate the results of your run. And I'd like to access it and see how did my run went, because I've saved some information during the run. And it's a web app. So how can I have a look at this? And this is what we'll be looking at with the Jupyter proxy server. Okay. So that's what I already said. So what is the Jupyter Server proxy? So it's a reverse proxy mechanism that is already, once you've installed it on Jupyterlab, and that's the case for the Nesi instances, you can transparently use it. It's interesting to know that this is actually the piece of software we use to deploy the virtual desktop MATLAB on the RStudio web apps on top of Jupyterlab. So that's what we're using under the hood for this one. But from a user perspective, you can use it with any web app. And here is how you would use it. You would use the URL of the Jupyter on Nesi /user/your Nesi login. So in my case will be Riom, for example, /proxy/ the port number. So when you run a web application, usually when it starts, it will tell you, hey, I'm running on localhost colon, and here is the proxy number. So that's sorry, the port number. So that's the one you want to use and inject here. I strongly recommend not to forget the trailing slash. I've been bitten by it a couple of times where I believe like, it's not working. Actually, it was just the trailing slash missing, and the underlying web apps was not happy about this. So typical example will be here that you can do jupyter.nesi.org.nz/user/, let's say my user is doich, it would be doich/proxy, and well, let's say I have a TensorBoard web app application running on 6006, which is the default port that will be here. An additional trick, which is good to know, and I won't demo it today, is you can actually you can reverse proxy a web app which is running on another node and then somewhere else on the HPC, but you need to give the hostname or the IP before here. Typical use case will be, I don't know, let's say you're running something with a Dask scheduler on it, and it has a Dask dashboard running on it. Then you can actually transparently have a look at it through your another Jupyterlab session, as long as you know where it's running. I want to highlight here that this is one of the many tools you could be using for this. Of course, I know that people may be familiar with SSH tunnels. That's another tool. So I'm just trying to highlight different options here that can be useful. But okay, let's go back to the demo and see how that can help us to solve our TensorBoard issue. Okay, so the first way let's clear that. I'll show you is, let's say I want to run my web app here, TensorBoard, in the command line interface. So TensorBoard here, I've installed it as part of my Conda environment. So actually, I'll activate my Conda environment. Up. And then I'll start the TensorBoard application. And I need to specify where are the logs that I want actually to display. So in that case, they are in my results folder and logs. So if everything goes all right, it should start, maybe complain with a couple of warnings and tell me what's the port number it will be using. And then we can see how we can craft the URL to actually access it. So I hope it's visible for everyone, but here you see that it says, oh, I'm running on localhost. So the very same node where my Jupyterlab session is running on port 6006. So I'll open a new tab. Up. I will copy paste, because I'm a bit lazy here, up my URL, and I'll say proxy / and the proxy number. And here, there's nothing. Yeah, because actually, as I said, I forgot the trailing slash. So let's add it back. And now, that looks much better. So now we have actually the TensorBoard, which is running, and that's the one that I've started in the terminal on the on this panel. And here, for example, let's say, so as I mentioned, I was running many runs of my model fitting, and one cool thing that you can do, for example, is you can use what's called a parallel coordinate view to have a look a bit at all the results and the different hyperparameters and what are the accuracy. So here my target value, and then you can explore and see, oh, okay, these ones will work better and this one work worse, for example. So that's one way to access transparently a web app. I'll kill that one now. And just for, do I have time? Oh, yes, I have the time, I think, to show that. So for TensorBoard in particular, there are a couple of other tricks that you can do and which I find quite practical. So am I in the right one? Yes, I'm in the right one. Okay, so TensorBoard can also be loaded as an extension in a notebook. And if people are familiar with this, and if you tried it on Nesi, it won't work out of the box because you need to tell the TensorBoard extension where to look for. So where is the proxy? And that's probably a similar pattern that you may encounter with other applications. So it's good to be aware of how to fix these sort of issues. In this case, for TensorBoard, the trick is to set up an environment variable before loading the extension and to say, hey, by the way, this will be run via a proxy, and here's the proxy URL. And here, I've been a bit cheeky because I've used another syntax as the one I've been presenting before instead of /user/mylogin/proxy. You can actually use another one, which is user-redirect, and that will replace, actually, then I don't need to enter manually my login. And here it's a placeholder for the port, which will be used by TensorBoard. So I will first make sure that I have a functional kernel. Forgot this. So then I'll define this environment variable, load the TensorBoard extension, and start with the magical command percentage TensorBoard. I will start it and launch the TensorBoard. And when it's ready, it will appear within the notebook. So here I've increased a bit the font size, so it's not very nice, but okay, that's the one. And I think that's it for this part. I'll just, as we have a bit of time, I think I'll take a couple of questions if there are some now, before we conclude the webinar.
Maxime, if you have the Google Doc in front of you, there are some comments and questions in this for this session which have been answered already, but if there's anything you might want to add to that.
Okay, let's have a look. Okay. Yes, so Annie is asking the question, so you can basically use papermill to adjust parameters in the Slurm script instead of constantly altering the markdown file. Yes, exactly, that's the case. And for me, it's really a tool to make sure that this will be my typical workflow is I will make sure that my notebook work, and making sure that I've defined some parameters at the very beginning that allow me to sort of adjust the computational requirements of my notebook. So make sure that it works on small data sets or very few iterations. So lowering the amount of resources I need so I can run the full notebooks in a couple of minutes, iterate quickly, and just making sure it runs. And once it's ready, then I would have wrap it into a Slurm submission script using papermill to actually say, I want to rerun the very same notebook, but instead of having these sort of toy cases, I want the real case, which is of interest to me. That's one first thing. And also, it's probably a bit of a digression, but I'd like to mention that the code here for this demo, which is available online on the Nesi GitHub, also contains an additional demo for people that will be curious to run it, where I used a workflow management system called SnakeMake to actually have multiple notebooks that I run in a sequence and that depend on each other, and having SnakeMake to actually call the command and call slurm by itself. It's a bit more advanced, but if you're curious to see how all these pieces can fit together and give you a sort of a nice path from interactive jobs to actually a fully multi-jobs workflow, that can be quite nice. And as a side note, we also provide training on workflow management system, for example, the SnakeMake at Nesi. We have one coming soon, but it's already fully booked. But if there is some interest, we'll definitely organize another one. So don't hesitate to tell us if that will be of interest for you. Okay, so I will now switch to the concluding remarks. So I think I already said a couple of times that the code is available. Again, if you're interested in this sort of webinars or other training events, I really recommend joining the mailing lists to know what's happening in the Nesiverse. If you want to find more recordings of webinars or teaching material, you can go to our YouTube channel. And as always, any question, suggestion, or feedback are more than welcome. We adjust our services to you, our users. So we want to know what you like, and if things works, we like to know. If things don't work, we also want to know, so we can improve. So yeah, so never hesitate to contact us at support@nesi.org.nz, and you will be put in touch with the right person to answer your query. And yeah, and thank you for everyone who attended this webinar, for your attention. It was very nice to have you here today.
Thank you so much, Maxime. Although we've gone through the Google Doc questions and anything else that you might have added in there, anybody else who might have any questions, comments, or any discussion topics that you might want to bring up, please feel free to unmute yourself and go ahead. Ron, yes, the recording of this session will be available on YouTube, and you would get an email as a registered attendee. You would get an email with the link and every other detail that you might need. Thanks.
Okay, so I think everyone can have a couple of minutes back.
Yeah, we're finishing early, so early lunch for everyone. Yeah, looks like we are done. So thank you so much for your time, everybody. And please make sure to go through all the resources that Maxime has listed in this last slide. And we will make sure that we get the recording out to you as soon as possible. And yeah, looking forward to seeing you in any of our future events. Yeah. Thank you.